Thank you very much for inviting me for giving this talk. Today we'll speak about the atmospheric escape processes and the planetary atmospheric evolution from misconception to challenges. And we'll see that it has a very specific objective here that is really within the objective of the whole community. But first, I'd want to thank all the people who helped me for doing this work, and what that work is basically the summary of a big review paper that has been published last year with the Living Breathing Planet. Okay, so the motivation we want to speak about atmospheres, and we want to speak about atmosphere both in the solar system and both in exoplanets. And the big question we are having, it's for NASA. One of the big questions is what is the habitability? Can we detect habitable world around other stars? And what is the evolution of in the solar system that led to the atmosphere of our planet, and why they are so different? Um, we know also that the exoplanets are laboratory for different kind of atmosphere, and they are both able to show us something new and able to make us better understand what is going on in our own solar system. And one of the big questions that we hope that exoplanets will help us to solve is that if it is really possible to what is the effect of a magnetic field on an atmosphere, and if it is really possible to shield an atmosphere with a magnetic field. So we have also a big astrobiology objective with the work, because if you want to detect life around other stars, there's not a lot of options, and the big objective for us right now is to detect life from the effect from the effect it has on its atmosphere. So we need to characterize the atmosphere, but first we need to know if the atmosphere is present and how it responds to its star. So we are not doing a weird analysis of what's going on. And then we need to understand how that atmosphere evolve with time and along with its stars. So we really need to
Excuse me, Guillaume, Mats here. I think we are seeing your Zoom screen. So that means the slides are a bit small.
uh,
I don't know if it's only me or if it's the same for other people too.
yeah, no, I cannot really. No, I don't. I don't have. Maybe if I do that, is it better for you?
Now the slide disappeared completely.
Let me try to do
Yeah.
that.
And now it's a bit too big. There it seems. Now you have it. Yeah, that
Okay.
looks
Oh,
great. Thanks.
okay. Um, so yes, I was saying that we need to study the evolution of the atmosphere along with its star. And of course, we need to understand a lot of things, because we cannot just stop ourselves on the escape, but we have to understand that an atmosphere is basically a kind of an equilibrium. I mean, it's not really perfect equilibrium because there is some dynamics, but we need to understand the atmosphere as something that is a result of all the exchanges, outgassing, escape, some of the initial accretion, condensation, and evaporation. And if, for example, if the escape is too big, we won't be able to have an atmosphere. Or if we have only some condensation, no evaporation, no outgassing, we can also totally lose the atmosphere. So the escape is a big problem, but we have to remember it's only a part of the equation of having an atmosphere. So now that all of that is said, we need to really concentrate on where the escape happens, and it's in the upper atmosphere. Not to be confused with the upper atmosphere of meteorologists. We are really speaking about the thermosphere and the ionosphere. And some of the big thing to understand and to remember is that we have the scale height, which is something extremely important to look at how compressed the upper atmosphere is, and it's dependent upon the temperature in the upper atmosphere, and we often approximate with the exospheric temperature. Um, and we have to speak a little bit about the exobase, or where the scale height equals the mean free path. And then we have to speak about what are the main parameters that are influencing this upper atmosphere. So we have the question of the atmospheric composition, which we have a little bit be speaking earlier, and we can understand that the atmospheric composition, by affecting the temperature, will affect the scale height, for example. We have the question of the solar or stellar UV, XUV, the different particles, the field, magnetic and electric field. Um, and of course, we have to consider the processes, so the chemistry, which can change the composition, heating and cooling, the radiative processes, and all the dynamic processes of diffusion, conductions, and wind. So putting an example with the Earth, we can see that all of that together really affect the upper atmosphere. And when we look at what happened, really, we see that condition changes, and for example, that affect greatly the temperature of the thermosphere and the exospheric temperature of the Earth. So, for better understanding what is going on, we have been first looking at all the processes that lead to the escape. Because if we want to better understand the planet, we need really to look at how these processes exist and how that they evolve depending on the different conditions from the star and from the planet in itself. And it's really by doing that work that we'll be able to understand where the escape comes from and what is the actual impact of the magnetic field on a different, on a very specific planet, sorry. So I want first to speak about really the thermal escape, and then we'll go a little bit about the different exothermal aspect. Because the thermal escape is really what is at the heart of understanding the escape at the beginning. So if we take the Maxwellian distribution, so the distribution function of the atoms or molecules in the upper atmosphere, we see that there is a small fraction of them that has a speed that is above the escape speed. And if they are with the correct orientation, they can really escape the planet. And so if that escaping fraction is small with respect to the Maxwellian, we are in a regime that we call Jeans escape. And that's fine. We can easily approximate the escape function. But if we start to have a large fraction of that Maxwellian which can escape, it's a little bit more complicated. We have to look in terms of fluid, and we are really in the regime of bulk escape, or also known as hydrodynamic escape. So first thing, both of this escape are some of the main escape in the history of a rocky planet. Exception happen and should be treated carefully. And we have to remember that these escape processes are not shielded by magnetic field. They can have some small impact of magnetic field, but they are not shielded by magnetic field. Uh, for looking at them, we need to look at the Jeans parameter, which is basically the ratio of the escape velocity to the thermal speed squared. So it's an idea of the gravitational energy divided by the thermal energy. And we have, it's really a critical lever that allows to say, okay, this one is in gene regime, and the other one is in um, hydrodynamic escape. Um, so I'm going to go a little bit fast on that. It's important to understand that at Earth right now, when the solar activity is high, it's one of the main escape process for H. Um, and if we want to go back and try to understand the history of a planet, we have to understand that there is some isotopic fractionation from that process. Then if we go to the hydrodynamic escape, we have to understand that it's extremely important for the escape of hydrogen in the early rocky planet. And it's at the origin of isotopic fractionation of heavier gases than hydrogen. Um, so we have to be very careful when we speak about the history of a planet atmosphere. First, we have to remember to look at the thermal escape, and then we have to go to the exothermal escape, non-thermal escape. So the non-thermal, it's when we cannot approximate the particle distribution that escape by a Maxwellian as shown earlier. So we can look uh, at different example of this processes, but usually it's very discrete processes that lead to having a particle above the escape velocity. Sources are photochemistry, ion acceleration in different fields, then charge exchange and sputtering processes. An example for the photochemical escape is, for example, at Mars, it's really the recombination of O2 plus. And we have also some photochemical escape induced by photodissociation. What is a big problem for us, because we want to speak about magnetic field impact, is really the ion escape processes. And we have really two regimes of ion escape, magnetized and non-magnetized, because we often hear that a magnetic field, a global magnetic field, will shield the atmosphere. But no, we have processes like the polar wind that lead to the main source of oxygen escape at Earth, and that is really enabled by a magnetic field. Then we have also processes of charge exchange that help escaping ions that are trapped in a magnetic field. Non-magnetized ion escape are also extremely important, and we have typically the ionosphere swept by the solar wind, and we have all the ion pickup and sputtering. So we did a big summary of all this ion escape processes and this other escape processes that can be seen in that figure, which is in our paper from last year. And we have typical planets where these processes are important. So little problems still exist, but I wanted to go a little bit in the evolution of the atmosphere and look at what are the drivers of that evolution. And we have two: there's the stellar activity and the magnetic field. First, on the stellar activity, we know that a star changes with time, and its rotation and activity change. I mean, flares coronal mass ejections and solar energetic particle events will have a variation with time, a variation of their frequency and a variation of their intensity. And the flares, for example, increase the heating and ionization, so decrease thermal and non-thermal escape. Coronal ejection increase the solar wind, so it typically increase the non-thermal escape. But we have seen that if we increase Joule heating, we can also have a small effect or big effect when we are close in exoplanet on the thermal process. SCP, the large part will have a effect on the lower parts of the atmosphere, but we still can have protons that will lead to non-thermal escape. To better understand the evolution of this star and the typical stars that are interesting for the study of the exoplanet, we have a mission that has been proposed to look at their activity with the objective of understanding the evolution and the escape of planetary atmosphere. And this is the escape mission with Kevin France as a PI in phase A for the NASA SMEX.
5 minutes.
Yeah. For the role of the magnetic field, so let's go and have a little bit of a very simple look at our solar system. And I'm not going to speak about the giant planet because it doesn't make any sense to compare them with the terrestrial planet with our objective of habitability. So we see that the Earth has a magnetic field and an atmosphere. Mercury has a magnetic field. It's smaller, but it has no atmosphere. Mars has a remnant magnetic field and a faint atmosphere. And Venus has no magnetic field, maybe it had one in the past, and a massive atmosphere. So we cannot just say that a magnetic field is equal to an atmosphere in a naive way. We cannot just claim that if we detect an exoplanet with a magnetic field, we cannot say that that exoplanet has an atmosphere. So the thing that it's not a naive one-to-one process, but if we go further, if we try to understand better the interaction, let's look at what happened and do measurements. So we see that Earth, Mars, and Venus have similar escape rates. The escape above the Martian field are enhanced or reduced depending upon the conditions. We see that the Earth's magnetic field prevents particles going in low latitude, but increased precipitations and escape at high latitude. And that polar escape is really enhanced during a high solar activity. If we try to look at the Earth without a magnetic field, or with a very small magnetic field, so during the inversion, we see nothing that is really convincing about an enhanced escape. Of course, we cannot switch off the magnetic field and see it right now, but in the history, we don't see really something really striking. So we cannot really have a decisive argument whether or not the magnetic field protects the Earth from atmospheric escape, or if it enhances it. Because we see that a field protects some escape, enhances some other, and actually, I'm going to say that the question maybe Hill posed. When we see that when we put a graph of the mass and the UV XUV radiance, we see that these two are linked with the presence or not of an atmosphere. And so the magnetic field may be just a driver when we are at the limit between the two regimes. And so better question maybe to ask what is the effect of the magnetic field on the composition of the atmosphere and how it varies with the planet mass and the stellar activity. So as a conclusion, the escape is extremely important to understand the origin, evolution, and habitability of the atmosphere. And it's really important to address the activity of the stars. And we cannot say that the magnetic fields are shielding planetary atmosphere, but we know that they have an effect. And it's a very complex thing, and it's really our objective here to understand what is going on. So yeah, we have some paper on atmospheric escape and the impact of space weather on the planetary habitability. Thank you for your attention.
Thank you. If anyone's got any questions, would like to raise your hand or put them in the chat. I can't see any at the moment. Yeah, I was interested about this Proxima B that you hinted about. You said you had a couple of extra slides on that.
Oh, on yeah, on the magnetic protection. Yeah, so Vladimir did speak a little bit about the effect of the Joule heating. And I was going to speak about the paper by Cathy Garcia Sage on the escape due to polar escape. So ambipolar, we create an ambipolar magnetic field that lead to ion escape at Proxima Centauri B. And basically looking at, if we put the Earth at the location of Proxima B, we can look at the lost time of an ocean in terms of gigayear. And it can, if we take an opening of the magnetic field and with different exospheric temperature, so something that is realistic of 2 or 3 exospheric temperature of the Earth, then we can lose an ocean in a gigayear. So that's something quite surprising and basically not very positive when we want to look at atmosphere around M dwarf.
Okay, we've got one more question in the chat. It says, do flares and CMEs and SEPs have fundamentally different influences on atmospheric escape, or are they simply extreme versions of the usual energy inputs from stars?
So yes, they have fundamental differences, and it's really here the magnetic field is really very important, because with a flare we do not have an influence of the magnetic field, so the heating and the ionization will be on the part of the planet that is facing the sun. But when we start to have the stellar wind coming, so a CME, then it will be very different between a planet with or without a magnetic field. So without a magnetic field, we will be likely to create some processes that lead to escape, a little bit process like bulk escape or plumes and so on. And for Earth-like situation with the magnetic field, then we will basically compress the magnetosphere, and we may enhance processes like the polar wind.